In mathematics, integral geometry is the theory of measures on a geometrical space invariant under the symmetry group of that space. In more recent times, the meaning has been broadened to include a view of invariant transformations from the space of functions on one geometrical space to the space of functions on another geometrical space. Such transformations often take the form of integral transforms such as the radon transform and its generalizations. Classical context. Integral geometry as such first emerged as an attempt to refine certain statements of geometric probability theory. The early work of Louis Santillo and Wilhelm Blaschke was in this connection. It follows from the classic theorem of Broadened expressing the length of a plane curve as an expectation of the number of intersections with a random line. Here the word random must be interpreted as subject to correct symmetry considerations. There is a sample space of lines, one on which the affine group of the plane acts. A probability measure is sought on this space, invariant under the symmetry group. If, as in this case, we can find a unique, such invariant measure, that solves the problem of formulating accurately what random line means, and expectations become integrals with respect to that measure. We can therefore say that integral geometry in this sense is the application of probability theory in the context of the Erlangen program of Klein. The content of the theory is effectively that of invariant measures on homogeneous spaces of Lie groups, and the evaluation of integrals of differential forms arising. A very celebrated case is the problem of Buffon's needle. Drop a needle on a floor made of planks and calculate the probability the needle lies across a crack. Generalizing, this theory is applied to various stochastic processes concerned with geometric and incidence questions. See stochastic geometry. One of the most interesting theorems in this form of integral geometry is Hadwiger's theorem. The more recent meaning of integral geometry is that of Sigurdur Helgason and Israel Gelfand. It deals more specifically with integral transforms, modeled on the radon transform. Here the underlying geometrical incidence relation is seen in a freer light, as the site for an integral transform composed is pulled back onto the incidence graph and then pushed forward.